Hey guys, so as Greta has just mentioned, I'm James and I'm a contract software developer at YLD and I'm currently based at Trainline. Tonight I'm going to talk to you about how one can implement a worker queue using child processes, so how it's possible to take payloads of work that need to be computed and do so on external event loops and external Node.js processes, which can really help you increase your requests per second in the context of HTTP, for example. So here's a logical starting point. What is a child process? It's a process created by and belonging to a parent process, and it communicates with its parent either via a callback upon termination, or you can have more longer-lived processes which communicate via what's known as an inter-process communication channel, where the child can send messages to the parent and the parent can send messages to the child. And Node.js provides this functionality by providing a module called child process. So let's take a look at this module. So it supports running any command and creating an IPC channel. So for example, you could spawn a long-lived process. I'm trying to think of a good example of that. You could do something with streams in Linux, for example, and when that process writes to standard out or standard error, for example, the Node.js child process will receive emitted events detailing what's occurred. You can also run any command in a new shell using child process.exec. So that allows you to run any command again, but rather than sharing the same shell as the Node.js process, it creates a new shell with a new login. Or you can do it in the current shell using child process.exec file. You can spawn a new instance of Node.js specifically with IPC support using child process.fork, where you pass it a module name that will be run with the Node runtime, and it will have its own V8 instance, its own memory sandbox, etc. And that has an IPC via which you can communicate with the child process. And also the library supports synchronous event loop blocking process creation. So you have exec file sync, exec sync, and spawn sync. And what these will do is they'll block the event loop until the spawned child process is terminated. So you'd probably use this for CLIs or tooling, for example. So our focus for today, in order to implement our worker queue, will be the fork method. So this asynchronously spawns a new Node.js process that executes the script found at module path. And I didn't mention it here, but it does this asynchronously, so it creates asynchronously outside of the event loop from which it was created. And apart from the module path, it accepts two optional parameters. So args, which is an array of strings that are available via process.argv. So if you've ran Node via the command line, which I'm sure you have, and you pass it a module name, you can also pass it a string of arguments after the name of the script that you wish to run. And that will be accessible in the same way when you spawn a child process and give it an args parameter. And then the third parameter is the options parameter, which is just generally for configuration. So for example, you can override the current working directory of the process, you can override environment variables, you can override the pipes to standard in, standard out in case you want to read that input directly or transform it in some way in your parent process. And as I mentioned, the module will run with its own V8 instance, its own memory sandbox, and its own resources. And when you invoke this method, it returns an instance of a class called child process, which is the next slide, naturally. So child process is an instance of event emitter. So if you haven't yet encountered this API in Node.js, it effectively allows one to create an abstraction where one can emit events and consumers can listen for those events and receive them and handle them accordingly. So child process specifically, it's an event emitter, but it abstracts the IPC channel between the child and the parent. And the child process itself provides a send method for sending JSON serializable payloads to the child process from the parent. And child process is spawned with an IPC channel, for example through fork, our main focus for today, can send messages to the parent process using the global process object's send method, which is kind of analogous to the one on the child process prototype, and that has the same constraints. It's serializable with JSON, so it's got to be in the right format essentially. And both child process and the global process of the child emit a message event when data is sent and received between the two processes. So here's a simple example to whet our appetites. So the top code, that's the parent module. So the contrast isn't great, but that's kind of unfortunate, but the slides are available afterwards, so I'll show you that link and you can access them yourself if this isn't too clear. So what we're doing in the top script is we're requiring the child process module and we're destructuring the fork method from that. And then in the line below, I create a new child. So I declare a constant called child and assign to it the return value of fork. And into fork, I'm passing child.js, which is the script below. We'll get onto that in a second. And two more lines in the parent module. So what I'm doing is I'm using the once method on the child to subscribe to the message event, and what once does is as soon as that particular listener receives an event, it will unsubscribe itself, which is important because, as we'll cover very briefly later, it's quite easy to leak memory when you're adding event listeners to event emitters, so that can be a nice thing to do if possible. So we subscribe to that event, and when the child sends a message to its parent, it will log the message. And then finally, we invoke the send method on child, and we send it an object using the object literal syntax with a property of message and a value of ping, which is a string. And I'm an unintentional poet as well. So in the child module, I've said foo.js, but that should read child.js. So yeah, I was probably working on this quite late in the evening. So when this runs, we attach an event handler in a similar way using the once method on process. And when process receives a message, which will be a result of the child.send invocation above, it will log the message, and then it will send a message back to the parent process using process.send. And that's when this event handler, child.once, will be invoked. So why should we use child processes? Well, there are two key reasons that I think should convince you. First of all, Node.js is single-threaded, so we can avoid blocking our main event loop. So in a lot of cases, you're potentially doing local computation, or your services are quite simple, so you don't always need this. But if you're working with like a lot of requests and you're doing a lot of CPU bound operations, then you want to keep the main event loop as free as possible. And also we can make use of additional CPU cores and processor scheduling time using the kernel's scheduling capabilities. So as opposed to threads, which for example can be managed by language runtimes, when we're forking a new node process, it's a new operating system process, so all of those resources and allocation and scheduling are managed by the operating system kernel. So there are two approaches. The first is the cluster module, which is also provided by Node for free, and I'll just cover that briefly. And then the second approach, which will be our focus for this evening's talk, which is a worker queue. So firstly, the cluster module. It's an abstraction of child process that forks the consuming parent module as child processes. So in retrospect, I could have provided a code example, but it's available on the documentation. So typically you'd have a script containing, for example, your HTTP server, and you can import cluster, and you can call cluster.fork within that script. That's all you need to do. And it will take that very same script and create it for you as a child process without any extra work. And if you're using TCP or HTTP, for example, it will share the same port. And by default, it uses a round-robin approach. So when the master process receives a request, it will distribute it in a linear fashion around the child processes. So, okay, I've sent a request to process 1, process 2, process 3, process 4. So it's quite naive in that respect. But also, it does provide an API for forwarding messages directly towards the children you desire. But what I really want to get into is implementing a worker queue. So what is a queue? Well, typically it's a first in, first out ordered list. So if you look at the diagram on the bottom, which we'll go over in more detail momentarily, the rightmost item was placed in the queue the first, and therefore that will be processed before any others. So a worker queue will hold an in-memory FIFO queue of work that needs to be fulfilled. It assigns work to a pool of child processes, and a child process will process a payload and ultimately return the result to the caller. One thing I didn't mention here, but we're not going to cover that today, is that typically, or at least commonly, in worker queues you can prioritize and you can pause work and reschedule it, but that typically requires the implementation of a state machine, so that's for another talk, I guess. Oh, of course, and the diagram as well. So what's happening here is, so this request here, this is when some consuming code has called a schedule method, which I'll go over some code in a moment. And what this will do is it will push a request for some work that needs to be executed outside of the event loop onto this queue. And what will happen is, once the worker pool has a free worker that isn't processing anything, it will pull the head of the queue, it will pass the request to the worker with the payload, the worker will do what it needs to do based upon that payload, and then once it has a result, it will send that back to the worker pool, which will then forward the result to the original caller. So that was me talking a lot. I mean, I hope, completely relevant, but I hope you're, still awake and still with me. Are you?
Yeah.
Okay, I'll take it. Could have been worse. Okay, cool. So now we're going to look at some code. So I wanted to show you this in my editor, but unfortunately I was having technical issues. So major thanks to Joao for letting me use his MacBook. So I wrote a library to do this myself. It's still pretty much a proof of concept, as it says in the bold text, but I like to challenge myself. So here's an example of the API. So you import this function called createQueue. Just step out the way. So you import this function called createQueue. You then call that function createQueue with, this contrast is a lot better at least. You call createQueue with two parameters, a path to the worker script and the number of workers you want to spawn. Now typically you'd align this to your computer's number of CPUs or the number of cores. I mean, because this is down to the kernel scheduler, nothing's guaranteed, but that's typically like a good starting point, and you can fine-tune the number of workers you want to spawn from there. And then it's based upon promises, this library. So you invoke queue.schedule, and you pass it whatever payload your child process expects to receive. So this sorter script I'll talk you through momentarily, but it accepts a payload in that format, so a file name property with a string of a JSON file to load, and then it is a promise, so I'm using the async await syntax, so I'm awaiting this, and once it's been placed in the queue, then dequeued, then processed, then returned to the worker pool, then returned to the consumer, they will have the result, and that'll be done on an entirely separate event loop. Cool, and I think, I was going to show you the actual end-to-end test. And this is the actual implementation. So here is, it fits on the screen perfectly as well. So here's an end-to-end test I wrote when I was developing the library. So I wrote the tests first, and then I implemented the library around that. So I'm using the path module, which allows you to build paths to files in an operating system agnostic manner. So what I'm doing is I'm creating a string, to the file of numbers I want to sort. And this is quite a small file, just because it's an end-to-end test. And then what I do is I read the numbers myself in the test. I sort them just using the built-in sort method quite naively, just so I can assert it returns the right thing. So what I do is in the before each hook of my test, I create a queue using the create queue function. So I give it a path to the sorter script, which I'll show you in a second, and I create 4 workers. And after each test, I kill the queue, and what that will do is it will kill all the underlying child processes, so it cleans up all the resources, and the processes just aren't left hanging. And then what I do finally is, can everyone see this okay, by the way? Yeah, should have asked that earlier, but I'm pleased with that response. Okay, so it has one test case that says it should delegate an operation to a child process and return the result to the parent. So I schedule a payload to the sorter script with the file name of the JSON file I want to sort, and once that's returned, I assert that the object that's returned conforms to what I expect it to. So now you see how the high-level API works. You're probably wondering, okay, but what does the actual underlying sorter script have to do with this? So here it is. So I don't have any kind of abstraction on the child process end. So once you call queue.schedule, and you've created the queue based upon the process, because we asked the library to run the sorter module, what will happen is, first of all, the part that's relevant to us anyway, it will subscribe to the message event emitted by the process. And we have 2 parameters. We have one parameter, an object with 2 properties. The first is the file name. So that was the JSON file, and then a second parameter called request ID. So you need to pass this back, but we'll get into that later. So what I do is I do a read file using the FS module, and into it I pass the file name, the JSON file I want to read. If there's an error, throw the error. Otherwise, just call array.prototype.sort ultimately, and then use process.send to send the result back to the consumer. So if I go back, not that far back. So when process.send is called in the sorter module, it will resolve this promise ultimately, and result will be the array of sorted numbers. So let's actually step into the code. Okay, lib index. So this is the entry point. So this is the create queue function. So you can see it takes two parameters, the script path we want to run and the worker count. So first of all, I create the number of workers that the consumer of the method has specified. Yeah, absolutely. Sorry, guys. How's that, guys? Is that okay? Cool, excellent. Right, so scroll down a little bit. So I create the workers, and I also create a router as well, which I'll get into in a sec. Yep, so first of all, I create the workers. So I'm requiring fork from child process, as we covered previously, and I'm calling the create worker, which creates an abstraction of a worker. I'll go into that script momentarily, but more importantly, we're invoking fork from the child process module, and the script path that's passed in, we're running that in its own event loop, in its own process. And then I specify the standard input and output options just so you can see any writes to standard I/O in your child process in your parent, which is quite useful for debugging. And so I create the workers, and then I create this enqueue function. So there's this method here called create. I'll step into these momentarily, so I'll give you some more explanation. But I invoke the create router function, and I create a worker pool, which is the pool of workers. That's the abstraction with which the router interacts. And then also there's the killer, where it's a really sinister name, create killer, but what it does is for each child process, for each worker, it will kill the underlying child process. So let's have a look at, okay, so first of all, let's look at the worker. So it's a relatively, it's a class that relatively lacks in behaviors. It's more just a means of like holding the state that's required to run the process. So so it invokes create worker, and all this does for now is it just abstracts an instantiation of a new worker instance. And what this will do is it will hold the process in memory, or a reference to the process, sorry. It will, and the most, sorry guys, my microphone's fallen off. It's getting a little bit carried away there. There we go, does that sound good still? Cool, so apologies. So this run method is what's invoked by the router, and this returns a promise which inside generates a request ID. It attaches event listeners, and this should seem familiar, this .process.send, so that's the child process. It sends the payload with the request ID, which you may remember from the sorter script. So this is the listen method that's invoked. So if you're wondering why we need the request ID, it's because when you subscribe to a particular process, because it's long-lived, You could, initially I tried to use this.process.once because then it would clear the resources as soon as it received the message, but you might subscribe while another message is being received. So in order to eliminate any possibility of race conditions, I generate a result ID and I compare it to the result ID sent back from the child process. And if they match, it means you know it's the right result, so it means you can send the correct result back to the correct caller. So, just before I step into that some more, at the bottom of the method, I subscribe to so this.process, just to ratify, it's a child process instance. I invoke this.process.on and subscribe to the message event and invoke the result handler function. And on an error, I invoke the error handler function. So on a successful result, if it's the same request ID, if it's the response to a particular request, it will invoke this.process.removeListener, which will remove the result handler, and it does the same with the error handler as well. Because if we don't do this, if we keep running requests, what will ultimately happen is we'll keep assigning event handlers, and ultimately it will result in a memory leak, which means Node will run out of memory and our process will die, which we don't particularly want. And once that's done, we then resolve the promise with the result from the child process. So next, I've called this the router for now. I can't particularly think of a better name. So this essentially abstracts the queue of requests, and essentially, when you create a router, this is just under the hood, the consumer doesn't have to worry about this. It returns this enqueue function, so it's a higher order function effectively. And what this will do is, the lines of interest here are, it will add the request to the queue, and this line here will essentially kick off the listener. So while the queue has requests on it, it will invoke queue.poll, which is the oldest request that needs fulfilling. It will get a worker. Now, this is called worker repository, but it should be called worker pool. It was just a change of name. So this is the worker pool. It will get a pool from the worker repository. It'll get a worker from the pool. And the reason this is a promise is simply because if all of the workers are currently occupied, you need to wait until the next worker is free before you can process that request and then send it back. So once we have a worker, we run the request. We then, if it's successful, we handle the result, so we resolve the promise, and then also, very importantly, we release the worker. So if you see this line 9, worker repository.release worker, if you don't release it, no other request will be able to use it. So then you're effectively one worker down, and if you keep forgetting to do this, you'll just fill up the queue and block it until the process dies. So you release the worker, and then you resolve the promise with the result from the child process. So the queue itself, it's essentially a linked list. So create queue just instantiates linked list, and what this will do is, when you add a request to the queue, the head remains the same unless there's no head is falsy, then this new node is the head node. Otherwise, you shift the items up along in the queue, so you get the previous tail node, the new node becomes the tail node, and then the previous node, essentially its previous node is the new node basically, so you're managing that queue without too much complexity. And then you can access the values directly with the head and tail method. So one more thing I'll show you is the actual worker pool. So what this does is when it's instantiated, I convert the array of workers to an ES6 map, and it's keyed based upon, so the key is a reference to the worker, and the value is a Boolean to suggest whether or not it's busy. So if they're false, well, they're all false initially, which means they're not busy. When you request a worker with the getWorker method, it will try to get a free worker. Now this is linear, so admittedly it could, hopefully you don't have too many workers, so it should be fine. If it's not busy, you mark that worker as busy with this.workers.set. It's the map itself, and then you return that worker. And otherwise, the worker, there's a queue of worker requests where if there's not a free worker, it will pass this promise resolution callback to that queue, which means, remember how I said release worker was an important method to invoke? So if there's a request for a worker, if someone's called, if essentially someone's wanted to run a payload and no workers are free, what this is doing is, if there are requests for a free worker on the queue, it will take that worker, it will take the promise and it will pass the worker into it, so then other requests can then continue to use those workers. Otherwise, if there's nothing left to process for now, you mark that worker as free, so you set its reference in the map to false. And that is essentially an implementation of the library. So in retrospect, I appreciate that was probably a little bit intense, but I will link to the repo is linked to in the presentation, so you can clone the repo and play around with it yourself and get a better understanding of what it's doing. And there are some examples in there for which I won't show you the code now, but I'll talk you through them, and I have benchmarks because I'm not going to, try to implement this crazy stuff unless I can prove, it's actually beneficial and it does what it's supposed to do, right? So the first one is sorting numbers, so perhaps not a real-world example per se, although you might be using Node to do some data processing. So this child process, it's the one I showed you previously. Because it can just process JSON files, I have one in particular that's 10 meg in size, and it's just a 10 megabyte array filled with numbers, and it uses array.prototype.sort. So in V8, if you have less than 10 items, it uses a quick sort, which is linear, which is fair enough, but because this is a massive array, it will use a merge sort. So the average complexity of this is O n log n, which means the more items you have in the array, it's not necessarily exponential, but it does ramp up a little bit the the complexity required the more items you have. So that's not the kind of thing you'll want to do on one event loop, otherwise you're going to hamper how much data you can process at once. And here are the benchmark results. So I spun up 4 workers, although just to ratify, the main process will take up a core itself if it's assigned by the kernel in that way. On a 2-core CPU, what this benchmark script essentially does is it will try to run in parallel in this child process. I think it was about 10 concurrent requests to sort numbers files, and with one worker it took about 20 seconds to sort the file maybe about 10 times. As soon as I introduced a second worker, this dropped to 12 seconds, so using this approach I was able to almost half the processing time. And then if you have a look at the 2-core CPU, when I increased to 3 workers and 4 workers, it went up a little bit, but I assume that's because on the 2-core CPU it wasn't able to schedule the time required too efficiently. But if you look at the 4-core CPU, and this had hyperthreading as well, so I could have effectively gone further if I wanted to. It went from about 13 seconds down to below 10. Between 2 and 3 it stayed the same roughly, but then it dipped again for when I had 4 child processors. So evidently, the more cores you have, the more child processors you should consider using. And then I have a more realistic example for what we might do in our day-to-day jobs. So React server-side rendering. So the reason I got onto child processors was simply because I used to work at an e-commerce company. We did server-side rendering, and because the business wanted us to render 90 items in React on the server, which I recommend you don't do, but they weren't flexible, we investigated this approach. So unfortunately, it didn't come to fruition in that workplace, but I've taken the idea a bit further. So if you use, hands up, how many of you are familiar with React? Pretty much everyone, okay, awesome. So React server renderer, so the React DOM server renderer in the React DOM node module, it's CPU bound. So if you're rendering HTML constantly, you're going to block your CPU. So I mean, you can cache like the markup at, you know, the memory level, or like in some Redis layer, or, you know, even using Akamai or something at like another level of abstraction. But if you're working with really dynamic data, this isn't always possible. So what I would do, this is in the repo as well, is when I wrote a server and when it received a HTTP request, it would invoke a child process using the worker key. It would use React DOM server.render to string in the process, and then send the markup back to the parent, which would send that HTML back. And here are the benchmark results. So I only ran this on a 4-core CPU with hyperthreading, and only went up to 4 workers. But I should have mentioned as well, I ran 10 concurrent requests here, and over a time span of, I think it was about 30 seconds. So what that means is, over 30 seconds, launch 10 requests. When one resolves, launch another request. And this is HTTP requests, by the way. So with one worker, I was able to serve 200 requests per second locally. With 2, this went up to about 360. Stayed about the same for 3. I think, again, this is how OS X in particular, or Mac OS, sorry, allocates processes and CPU time and that stuff. But then the 4th, when I added a 4th worker, it went up again. So from 1 worker to 4 workers, I was able to double the number of requests per second my HTTP server was able to provide. So the benefits are completely tangible. So we're almost done. 2 more slides. Firstly, I want to point out some caveats to you. So as I mentioned, the CPU core and scheduling time assignment, they're managed by the operating system kernel. So you don't necessarily have control over that. If you look at threads in Java, for example, you can do prioritization and stuff. And the child process API, I think it does allow that to an extent, but it's really up to the kernel scheduler, so you don't have much say necessarily. Secondly, as I also mentioned, the payloads you send via process.send have to be JSON serializable. So don't send massive payloads over a message, because that will all have to serialize, and that will hamper your performance. So instead, if you can, you know, send file names, for example, or, you know, other flags, things that are a lot simpler, that will help the performance. Also, you have to ensure you're removing event listeners. You may remember I showed you where that was taking place in the worker abstraction. If you don't remove the event listeners and you keep receiving requests, then ultimately you're going to run out of memory. And one more thing, which is a bit less technical, it's the actual cost. So in my implementation, the worker count doesn't scale depending upon the necessity and like the traffic. Instead, the number of workers stays constant. So if your service sometimes receives hardly any requests and you're using all of your cores, then that's potentially going to cost you money on AWS for resources you aren't using. So I'd only use this approach if you're receiving a lot of traffic. Otherwise, you'd either want to scale up or down the workers, or you'd want to scale at some other level instead. And one more thing before we wrap up. There are some alternatives to which I'd like to draw your attention. So firstly, there are native abstractions for Node, so you can interact essentially between Node and libuv, which is the asynchronous I/O layer used by Node.js. However, it requires a knowledge of C++, which I don't have in much depth, so unless I start learning C++, which I want to do, that rules me out as a potential user for the time being. You can use the Stream API as well. So Node is heavily built around streams, and that provides some capabilities for piping streams and operating upon data asynchronously. And also, one task-specific library I wanted to mention was Rapscallion. So this is an asynchronous an asynchronous Node.js stream-based renderer for React. And compared to the stock renderer, on some hardware, I think there's about a 30% performance improvement. So if you can find something specific to your use case, that might be beneficial. Cool. Well, thank you very much for listening. I see in retrospect that was a bit intense, but I'm absolutely happy to field any questions you may have.
So in your library, what happens if the worker crashes?
So if the worker crashes, I did look into error handling. So the child process, or like processes in general, like they do have an error event that's emitted, but you have to, I think if you throw an error in the child process, it will send that back to the parent. However, one thing interesting I noticed was I was throwing a new instance of error, but I'd get a JSON serialization error. And I think what it's trying to do, I need to look into this further, I think it's trying to somehow serialize that error instance, and it can't serialize it to JSON. So I can't confirm for sure, but I think the idea is you'd probably send a JSON payload back that marks it as an error.
Have you considered how to extend this, how you could extend it to work across multiple servers and distribute the load over other servers?
I haven't yet. That is an incredibly interesting question. So, I mean, I wouldn't use this in isolation. I'd stress that you'd probably want load balancing on the HTTP level as well, for sure. This is just one layer of asynchronous request management you can implement ultimately. Yeah, I haven't given it much thought, so I'm sure like someone on the internet could give you a much more rational answer than I could.
I might have missed it, but is there a way to get a list of all of the current child processes your current processors supporting?
Good question. I'm not 100% sure, unfortunately. I didn't need that in my travels, but yeah, I'm afraid I don't know of anything built in.
So what is the footprint actually of one of the processors? So the processor started again V8 and all that.
So a lot of don't knows to these questions, I'm afraid. So unfortunately, I didn't have time to look into this. Certainly with fork, because you're creating an entirely new process of Node, I think it lives in the same shell, so you don't need a new shell login. But it has its own V8 instance, it has its own memory space, so it will like potentially, I won't say double your memory print per se, but for each component you have of a node process, you need like respective ones for each child process. So if they start to use a lot of memory, they can as well. So I think this links back to what I was saying about the cost. Unless you have things where you're receiving requests all the time, you'd either scale like the processes down, or you'd find an alternative approach. But unfortunately, I can't give you a deeper answer.
So existing now has streaming rendering. Have you looked into that at all?
I didn't realise it had it built in actually. That's very cool because I encountered Rapscallion in probably around React 15, but that's very cool. I know about component did catch and the fiber stuff. I wanted to look into fibers for this and prioritization, but again, time constraints. But thanks for bringing that to my attention. I'll take a look for sure.